this particular research, we look at protocol gateways. So these are like tiny device, like this one you see on screen, that are widely used like in all the facilities worldwide, and they play a very important role. So we decided explicitly to focus to these devices to detect like potential vulnerabilities and potentially also find like solutions. So this is a joint work between myself and a few colleagues at Trend Micro, as well as independent researcher Luca, that help us with the firmware reverse engineering and so on and so forth. Yeah, so let me start by saying that nowadays industrial networks are a very complex ecosystem. So you have the enterprise logic, where you define what your production side need to produce. Then you have a control network that normally runs on TCP/IP, where you have like databases. You have the machine for controlling like the production itself, where you define how many pieces you want to produce and so on and so forth. And then you have a field bus network, which is what actually is connected directly to the machine that does basically the production. And usually this field bus network run on serial, so like very old, technologically old basically networks. It's actually more complicated than this, because each of these three layers, enterprise you can see on the left, cloud in the center, and field network on the right, they rely on different other protocols. This is because there is no real standard, so each vendor basically does what he wants. So this complicates heavily the communication inside your production site, especially when you have like more production sites that you want to connect. So as a result of that, the market came out with these devices called protocol gateways. These are used to basically transform one protocol into another, and there exist different type of these gateways. But what they all have in common is that they are pretty small, as you can see on screen. You can keep them like basically in your hands, and they have one or more interfaces. And they actually, as I said, they do basically translation from usually from Ethernet to serial. For example, they're used to connect the control network to the field bus network, where you actually have the PLCs and the machines. But could be used like in a different other scenarios, like if you want, for example, to control some sensors or some motors remotely, for example, via GSM, that's also possible as well. This is a typical installation, as I was mentioning. So you have a device here in the middle of the screen that basically is used to connect the control network to the field bus network. And in this specific case, the device, the gateway, translate from Modbus TCP, which is the TCP/IP implementation of Modbus, to Modbus RTU, which is the serial implementation of Modbus. For those that are not really expert, Modbus is one of many ICS protocols, so protocol used to manage control networks. And here, as you can see, what the gateway does, it takes the command generated by the operator on the HMI interface, so on the control server if you want, and basically converts such command down to the PLC, which is sitting on the field bus network and behave as a Modbus slave. So you receive the command from the master, and they propagate such command down to the different sensors, engine, motors, thermometer, and so on and so forth. So this gateway plays a very important role, as you can see here. So even if it's very small, it's actually very, very important in the production side. And the problem we have observed is that there is a general misunderstanding, if you want. So the fact is that most of the people think these devices are just a piece of hardware, so they don't really run a fully fledged operating system. Well, actually, it's not true. They are very powerful. They come with a very fast processor and has a lot of features. So you can consider them as a fully fledged like system, not just like a small tiny device. And on top of that, it's not true that they perform just secondary tasks. but actually they play a very important role, like in your industrial network, no, in the core of your industrial network. So as a consequence of that, we have seen that these devices tend to be overlooked. They might be not indexed in the assets of the important devices of your company, and as a result of that, they might not fall in like your patching updates. So they might not necessarily patch. They might not be monitored for problems. They might be misconfigured as well, or configuring with the default configuration. So in our research, we decided to do something new. Thomas Rowe, you can see here on the left side of the screen, did a presentation at Black Hat a couple of years ago where he looked into the security of these devices, but only related to the security of the device itself and not on the translation. So for us, not much interesting in knowing that the device might have a vulnerability. That's okay, but what's the impact of this vulnerability on the translation? So we are really interested in understanding how a certain language, for example, A, you can see here, get translated into another language. So what really could go wrong with the translation itself? So as a result of that, we did an analysis which is vendor neutral. So we didn't finger point against specific vendor, but we look at the technology from a general standpoint, right? And we focused here to Modbus because it's probably the most used ICS protocol out there. Even for these devices, as I said, they might support other ICS protocol like Profibus, CAN bus, and so on and so forth. So we found problem with Modbus in translating from Modbus to Modbus. So I guess if you look at translation, for example, from Modbus to Profibus or to even something more different, there might be even more problems. These are the list of gateways we consider. So there are some that are from the east side of the world, one that is European, and some that are from US. They are all pretty much similar to each other. What changed the most is that they fall into two macro categories of gateways. So those ones that are real-time, so that does a real-time translation of a network traffic, as could be like the ADSL router or the fiber router you have at home, that translate one inbound packet into one outbound packet. And those that are a bit more complex, that use something like internal caching mechanism for doing an asynchronous translation. I'm going into detail more about this second category of gateways that are called data stations. But what you can think, basically to summarize what we do, they do not wait for a read request. For example, you have a master that want to read some data out of a sensor, for example. What the master do is to trigger a read request for the sensor. So this data station, they do not wait for this read request to pull data out from the connected sensor, but they continuously request information from the sensor, they keep an internal cache, and then they update the master when it's needed. As you can see, it's more complex, and this is made for performance reason. Not going much in detail, but data stations normally are more efficient than real-time gateways. They cost even more. They're more sophisticated, but they might also have additional problems when compared to the real-time gateway. And let's look at how we did our research. So the general idea is that you have a researcher like myself or some of our colleagues that want to test one or multiple gateway. Okay. So what the researcher does, he instructs what's called a Fuzzer. So the Fuzzer is basically this code that generates test cases to trigger potential vulnerabilities in the translation. And it also looks for conditions that might indicate problems with the gateways. So that's why the Fuzzer also does what we call the crash monitoring of the gateway. And what the gateway does, it translates the inbound test cases into the translated traffic down to a simulator. So that's also very important. So the simulator, for example, could be like, for example, a simulated PLC. If you are translating from a master down to a slave, or it could be, for example, a controller if you want to see the translation from the slave down to the master. I'm going to talk a bit more about the importance of the simulator later in the presentation, but keep in mind that as part of all the architecture I'm going to show you now, the simulator plays an important role to make the gateway basically operational. So what happens then? We have a sniffer that collects the data on the outbound interface and forward such data for comparison to an analyzer. So the analyzer compare the traffic generated from the Fuzzer, which is the inbound traffic, with the outbound one, and automatically trigger some alarms if a translation is wrong. So if the gateway did some mistakes in translating, or if the gateway dropped some packets because it was not able to do the translation, and so on and so forth. So let me talk now about the simulator. So here on screen you have two simulators that we used, that we actually reused from what we found online. So these are called QMod Master and PyMod Slave. So I want to also acknowledge the developer of these two simulators because we made use of their code. So the first one on the left simulate a master, like a controller. Like that one on the right simulate a slave, like for example a PLC that is connected to a sensor or to a motor, for example. So the first master is connected via TCP IP. You can see here that's the IP address of the gateway here in the middle. So it's connected via TCP IP to the gateway, and the slave is connected via serial, as you can see at 38 kilobound, that's the speed, is connected via serial to the gateway. So what the master does here, this example, he requests a read coil command. So the read coil command basically is a request in which is requesting some data out of the memory of a PLC. So in this case, he's requesting 5 coils, so 5 like cell of 1 bit if you want, or 5 memory location, starting from address 0. So in this case, he requests these 5 address, 5 memory cells, which have such address you can see on screen, 10101. Such value is then reported back to the master. So this is how a simple Modbus request of read, basically is. So if you look at the payload, so actually what happened actually on the network, you can see that the master itself generates a packet you can see here that is composed of a header and the payload. So the header are information related to the protocol itself, while the payload is actually the request. So these 5 bytes of payload represent a read request having function code 1, the starting address, which is 0, and the quantity of register, which is 5. So this packet is sent by the master to the gateway. What the gateway does, it gets rid of the header, it takes the payload, it computes the checksum for the serial communication, and it builds what is called the Modbus RTU packet. So this one on the right is a Modbus RTU packet. This is sent down to the slave. The slave replies with the register values 15, which is the value of the memory at such address. And what the gateway does, it basically translates back from RTU to TCP. As you can see here, it basically does the opposite. So this also explains how the translation from Modbus TCP and Modbus RTU is implemented in the gateway, both from from TCP to RTU and from RTU to TCP. So let's look briefly at the Fuzzer. So I'm not going much in detail here because we don't have time, but there are 2 macro categories of Fuzzers online. Those that are mutation based, that have ability to learn about a protocol if a protocol is unknown. For example, if you want to fuzz proprietary protocol, and those that are generation based, that works well if you know the specification of a protocol, which was actually our case because Modbus has a known specification. So for that, we used a modified version of BuFuzz, which allow you to, as you can see on screen, to define specifically how the protocol look like and all the fields of each, for example, message of a protocol. For example, here you can see on screen, this is for writing a single coil. So if you want to change a bit On the PLC, for example, you're going to request a write single coil request. So this is, you can see on your screen, you have a header with the different header fields, you have a payload with the different payload fields, and so on and so forth. Here again, if you're curious about how this works, you can read the paper or just ask me. But what you can do, you can configure, sorry guys, you can configure basically anything. Like you can specify which field you want to fuzz. If you want to do like, if you want to fuzz all the space or only part of the values, of the potential values for a field, and so on and so forth. So it came very handy for us to generate basically all the combination of messages we want to generate to trigger vulnerabilities. You can of course instrument the fuzzer as well, as you can say, as I was saying before, so you can monitor for particular conditions. For example, here you have an example in which the fuzzer detects a crash of the device. So you can do that. You can also specify what happens if a crash is detected. So in our case, we are automatically rebooting the device, for example, by using a network power stripe, which is like a device that automatically boot on a device. So if a gateway goes down, we ask the network power stripe to bring the device up, and we continue the fuzzing. On top of that, we had Wireshark for monitoring Modbus TCP, and IO Ninja, which is it's a fantastic tool. We use it for monitoring the serial interface, so Modbus RTU. And then we had the scripts for data normalization in order to compare these two protocols, which are different at the end of the day. And then we had the analyzer, as I said. So the analyzer does automatically correlation of inbound and outbound. So for example, in the translation from TCP to RTU, he verified that the Modbus header is correctly removed. It verified that the payload that you have down here in red is correctly encapsulated in the Modbus RTU request. He checks that the checksum is correct. He checks that all the packets are propagating from inbound to outbound interface and in the right order. If it's a real-time gateway. If it's a data station, it keeps track as well of the request and response by using what we call nonce. So I'm not going to detail here, but we have also technique to automatically detect mismatch or packet drops for data station. Yeah, so it's about the introduction. Let's now look into findings, and I'm going to tell you what could go potentially wrong with such important device in production sites. So first is resource exhaustion. So this is the case when the device does mistake in handling traffic, and by, for example, the reboot, it might hang on the TCP/IP stack, it might hang on the translation process, and you can consider this as a denial of service attack, because if you have an attacker sitting anywhere in your corporate network and he is able basically to cause a resource exhaustion problem, he can bring down, for example, a production line, and he might, for example, ask for a ransom in case of attack. So here on screen you see, for example, device that has been running since, as you can see here, since 15 minutes and 45 seconds. What we are fuzzing it, we are generating test cases 1 per second, so not much. In fact, you can see that the bandwidth is 23 kilobytes per second, so it's not much. Even if you were not actually dosing the device, but only sending malformed packets one every second, the device crashed. You can see that here you have an instrumentation algorithm that detects the crash. You can see that the web interface of the protocol gateway is not reachable any longer. And here we can see that the power socket as well detects the device to be off, and we automatically reboot the device thanks to our instrumentation. We brought the device up. So you can see the device is up since 5 seconds now, and we continue the testing. So this is, for example, a case in which we found one or more packets that create problem to the device. Let me give you now an example of one of these packets that was triggering actually a reboot of a device on Red Lion, which is one of the gateway we test. So let me open here. I'm going to play for you now here this video. So here you have that's the device which is currently operating here. Now I'm going to send the packet in which I'm going to, so my packet basically consists of a read request for an address which is 0. And in this specific case, this data station here has a problem with indexing these values. So 0 falls out of a memory range of a device, to make it simple. And you will see that basically the device reboot. Yeah, you can see that there were some red LEDs. You can see now that there is a blue LED that is basically the rebooting process. The device detect the testing script detect that the device was down. Down here in the lower part of the screen, you can see the logs coming from the device, and you can see there is a drop of 20 seconds. So that's the time that took for the device to be reboot, no? To come back online, basically. So now we send the second packet, which is very similar. The device went down again, and basically the same things happen. So we don't receive any more logs from the device, like a ping, right, from the device, but we had to wait basically 20 seconds for the device to be rebooted. So here is a very easy example where we show basically that with one packet we are actually able to reboot the device. So that's very severe. Let's look now at translation bypass, which is actually the core of our research. So we start by analyzing, but evaluating the ability of the different devices to drop malformed packets. So what we did, we generate with our Fuzzer a set of thousands of malformed packets. We send this list of packets to all the devices, and we test their capabilities in dropping the set of malformed packets. And it turned out that more robust devices, these ones that are in green the screen, they can filter 30% of malformed packet, which is good. They have good filtering capabilities before the translation, while one device was filtering none of them, So we look more into this device, which is called Nexcom Neo 50, and it turned out that a lot of these malformed packets that didn't get filtered correctly, they were made voluntarily in a way that had a length which is different from what's specified in the header. So here you can see on screen that the header specifies a message length of 11, while actually the length is of 6 bytes only. So that's an incongruency, So there is a mismatch between the length of the payload and what's expressed in the header. So in this specific condition, what the device does wrongly, instead of dropping the packet or correcting the value of the header, it does a straightforward, it does basically a forward of the packet as it is. So it's not actually never dropping the packet or correcting the packet, and is not translating the packet from Modbus TCP to RTU, but is basically forwarding the packet as it is. Here you can see an example where an attacker that took control of one of the machines of the control network, for example, the historian, which is basically the database, or could be the engineering station anywhere in the network. He sent one packet to the gateway, and I'm going to show you now what happened on the field network, so on the production line operationally. So the request that the attacker sends is a read request. So it's a request for reading out of a PLC a certain number of registers. In this case, it's just 70 registers, but could be anything. So this read request bypass the SES firewall that we assume a conscious and intelligent and smart OT engineer has installed to prevent malicious packets like write, like for example packets when you set basically values on the field network to be transferred down to the PLC. So the SES firewall normally allowed read requests, where you read data like from sensors on the production to monitor the production, but does not allow, for example, a write request, where you reconfigure a motor, a relay, or something like this. So here I'm going to show how this read request actually get automatically converted by the gateway into a write, which is completely wrong, because the gateway should take your request, which is a read request, convert into the same read request on a different protocol. But what happened here is that this packet, which is a read input register, if you apply the Modbus TCP semantic, become a write multiple coil request if you apply a Modbus RTU semantic. This is because the packet itself is the same, but the packet on the RTU side doesn't actually own like a correct Modbus RTU semantic. So as you can see here, the content of the packet is the same, but the fields are different. So if you're really using the Modbus RTU semantic, the function code, which for Modbus TCP is here, is 04. In Modbus RTU is on the second bytes, which is 0F. So the transaction ID, which the attacker voluntarily made as 01 and 0F, become a write request for slave ID 1, right? Which is, I'm going to show now in the demo, and so on and so forth. So there are a bunch of other information I'm going to explain here, but basically the concept is that the attacker is able to convert a read request into a write request. So he can convert a legitimate request that easily might bypass all the ICS firewalls into a command that change the configuration of the production side. So let me give you an example, a video again of attack. So we are here. Yeah. So that's the video. So here you can see on screen. Let me go full screen. Yeah. Here you can see on screen the protocol gateway, which is called Neo 15. That's the web console. The gateway is configured to convert Modbus as a protocol from Ethernet to serial. So from Modbus TCP to Modbus RTU, which is exactly what I'm, visionary we have in the slide deck. Yeah. So now here on the backend, in the backend, I run TCP/IP for sniffing on the TCP side, and then I have this other tool for which is called bus monitor for sniffing on the serial side. Yeah. Okay, so here you have on the right side here, this one is called FTR Nexus demo. This is OpenPLC, so it's a simulator that simulate basically PLC, right? So you can see that this controller is basically receiving correct information from the thermometer. So that's the value of the thermometer, which is of the real thermometer. Is reading data out of the tachometer. Is also telling me that both the motor and the relay are operating correctly. So basically the production is correctly operating. So the motor is just based on the value of sensor like thermometer and tachometer. So what the attacker does here is send the packet I show you on screen is exactly the same, where he's asking to read 70 register starting from address D1 CE. Okay. So what happens, you have a gateway in between. The gateway take the packet as it is, forward the packet as it is on the RTU side, and the result of that is that the PLC disabled basically the relay. It disables the thermometer and tachometer while keeping the motor operating. So that means you have a condition where you don't have a loop that basically is monitoring the production, so like the result of what the motor is doing, but keep the motor running without monitoring. So that's super severe. And I'm going to show you here in the push request of the Modbus TCP, the packet, which is the packet generated by the attacker. And on the serial here, you can see that basically the packet that is received by the PLC is the same as the attacker. So the problem here, again, the gateway, instead of removing the Modbus TCP header, taking the payload, computing the checksum of the Modbus RTU, and doing actually an actual translation, it takes the packet, the original packet as it is, and it converting down to the slave. All right, so let me show you now let me talk, yes, I have a few more minutes. Let me talk about data stations. So these are, as I said, the more complex devices because they work in a synchronous way. So the result of that, you have two routines. So the first one basically parse the inbound traffic and use information from the inbound traffic to set fields in what is called an internal mapping table. And then this mapping table is used to trigger traffic on the outbound interface. In simple words, it's a bit more complicated than this. So suppose you have a data station that is configured as the following. So it's configured to propagate, to forward two requests. So one is to set a switch. So it's a call request. So you reset like a Boolean, like enable a switch, for example, an energy switch, whatever. And then you have another request that is configured to be propagated, which is set a temperature. This is a register, right? Because you're going to basically set, a number, right? So not a Boolean, but a number. So what happened here, the set software switch is configured to, is mapped to internal address 0, while the set critical temperature is mapped to internal address 2 and 3. What does it mean? It means that if there is a change in one of the first 8 bits of the first byte, then the set software switch request is triggered and the right coil is generated on the output interface. While if there is a change in byte number 2 or 3, at that point, a set critical temperature message is triggered. It's a bit complicated. So the problem here, there are different problems. So the first is that if a data station receives, for example, a write coil 0, you'd imagine that on the outbound interface there is a write coil 0 or on a different protocol. No? Well, actually, this is not the case. So 0 is used as an index in the mapping table. And then the corresponding function that is mapped to address 0 is triggered, which is something weird, but this is how this data station works. The problem is that there is no outbound there is no outbound checks and no even check of the function code. What does it mean? It means that the attacker can use, for example, write coil 0 to write to a mapping to the address 0 of the mapping table. And if in the mapping table at address 0 there is configured a write register, is able basically to trigger a write register by means of the write coil. So is able basically to turn a write coil into write register and vice versa, as you can see here on screen. And this is actually a problem. So you cannot go from read to write, as we have seen before, or from write to read. So you cannot really change read into write. But you can by changing one single bit, you can trigger a write register request. So let me show you an example here again. I'm going to describe you the scenario and then I'm going to show you the video. So here we have again a PLC, actually an HMI that control more things. So it's monitoring the temperature via real sensor. In this case, there are 42 degrees Celsius because it was summer when we did this experiment. And if this temperature go over a critical threshold, which is set in the PLC, an alarm is triggered. So it's very simple. It's basically like a feedback loop that checks that that everything is fine and there is no it's not too hot basically. And we assume that this critical threshold value is a protected parameter. So the OT engineer configure it, basically hard-coded in the PLC, and we don't want someone to change it, because if you set this critical threshold too high, so instead of 200 you set it 2000, you might not hit it, so you might burn something, no? While if you change it too low, like you said 20 Celsius instead of 200, then you would basically trigger a lot of false positive and block the production. So in the example here I'm going to show you now is we show how by generating one single request and one write coil, so we change one single bit, actually we can change an entire temperature that actually is protected by the firewall. So let me go back here. Yeah. Allora, let me show you first camera 1. Yes. So this is our configuration. So the black box here is the protocol gateway that is connected on the two interfaces on serial and on the TCP. So the TCP goes to the fuzzer or to the attacker node, while the serial is connected to our open PLC that will work. And this one is connected to all the different sensors. So there is a sensor for the temperature, there is the siren that is triggered when the temperature go over the threshold, and so on and so forth. So this actually is simulated real world installation. Yeah. So this is what happened on screen. Yeah. So first, we show you how an OT engineer set the default critical threshold parameter, temperature. He does it by using a write register request, okay, which is the right, is correct way of doing it, because you're going to set, as I said, a number. So use a write register request. And you set a value of 3000 because it's an integer, but it gets converted into a float because it's 300.0, okay. And this is what, and this corresponds to function code 6. So write register is function code 6. So in this scenario, the SES firewall is configured to only allow function code, to disable, function code 6, because you don't want basically someone to change such critical threshold temperature. What happened here, we're going to show how an attacker will use function code 5, which corresponds to a write coil request to change such values. So we change, use a write coil, you can see here on screen. We flip one bit, so the bit corresponded to address 22 in memory. And by doing that, we move up the critical threshold to 1800, you see, which would never be met. So this is super problematic. And the attacker can also do the opposite. So if we change, as you can see on screen, what we'll see now, if you change basically address 23, you basically overflowed, the address, the value, okay, like an integer overflow. So you bring basically the critical threshold down to negative, and as you can see here, the alarm get triggered, so it become green. Let me show you also on the camera. So here it's the camera that is basically showing the HMI and all the setup. It's running, yes, you see. So as soon as one bit get changed, a write register get triggered. This one bypass the SES firewall and allow basically to change a protected value. So I guess I have, let me see, probably 5 minutes more for sure, because I started a bit later. Let me briefly tell you, discussing a bit a few techniques we identified to leak the mapping table. What does it mean? It means that for data station to be able to perform such attacks in an efficient way, you as an attacker, you need to have a certain understanding of how the device, how the gateway is configured. So this is like a difference between like a SQL injection and a blind SQL injection, or any attacks in which if you have more information about what you are attacking, then you can have more efficient attack. So in this specific case, if you know how the mapping table looks like, so the memory, if you know the memory of the device, basically, then you can do a more accurate attack. So the first problem we found is that the admin password is encrypted with a nonce, so with a random value that is guessable. This is because during the initialization phase of the device, so for example after a boot, this v11, which is used in the randomization function of this nonce, does not come with an initialization vector. So it's always the same. So an attacker can basically steal this nonce, use it, and basically with that, you can basically guess the password and authenticate to the device, and then dump basically the memory of the device. That's one technique, this token credential reuse technique. The second one is the fact that the configuration itself is encrypted. So when an admin basically connect to the device and dump the configuration information, yes, it's encrypted, but the key that is used for encryption is part of encryption of the configuration itself. So you have basically the encrypted configuration, which is encrypted with AES, and then you have the key, which is part of the configuration. So you can basically take the key out of the configuration blob and just decrypt the configuration yourself. So we did that by using, you can use, for example, QEMU, and to run basically the AES proprietary library function from the firmware. Then you provide the key that you have in the configuration, in the encrypted configuration, and then you decrypt it. And you have access basically to the configuration file in a SQLite format, including the memory. The second one is an authenticated privilege escalation box we found in the web interface of one of our devices. So you can authenticate as a read-only user, like a low privilege user, and then you can trigger a common injection vulnerability in the form. Here you can see for a ping test. I'm not sure why the device run ping as root, but you can do that. So you can run a busybox telnet the daemon, and then you can connect in your root. At that point you can dump the memory. And the other one is a memory leakage we have found, in which we send basically a write multiple register request, where we specify a number of bytes to be read equal to 0. At that point, we can dump, as you can see here on the right, is a memory table of this device. We can basically dump part of the memory related to this portion where there is the table, and we can also guess basically. It's predictable. So I'm not going to detail here. It's more in the paper, but there is a way basically to identify the part of the memory that contain this mapping table and dump it. There are a bunch of other problems I'm not going to discuss for lack of traffic on the cloud. So how this device integrate with the cloud thanks to, for example, MQTT. So how they translate from Modbus to MQTT. There are problem with availability, the fact that you can reboot, you can change the default IP address of this machine. And there are also problems with different implementation of the specification. So even if Modbus is not a proprietary protocol, not all the devices actually incorrectly follow the specification of Modbus. To conclude, I want to say that OT engineers should consider security as an important aspect in their product selection. So modern protocol gateways, as well as other ICS related devices, come with some security features, like us, not all of them. So carefully pick your devices, and consider security as an important aspect in product selection. Do not rely only on one single point of failure. Like in a normal IT network, you have firewall, you have antivirus, you have IDS, IPS, whatever you want. But in the ICS world, normally you just have ICS firewalls. So that's not enough. So we have seen how you can bypass such devices. So you might want to rely on other techniques like active monitoring of the serial traffic. You might want to, do an automatic patching of the device, and so on and so forth. And this brings to the last one, which is correctly, configure and manage these devices. Because even if they are small and they are hidden, somewhere in your network, and you might even forgot about their existence, you need to, correctly configure them and actually patch them, because it's very important. So this is a list of vulnerabilities we reported to ZDI, the Zero Day Initiative, and we reported to the vendor thanks to the support from the ICS cert. Some of these vulnerabilities have been already patched, some won't be patched, so are actually 0 days, and some other will be patched in the future. So we basically overall we help vendors in realizing of this problem with protocol translation. And we hope our research will be helpful as well to the security community, as well as to IT and OT experts. So the QR code point to a URL that hosts the paper. You can also Google for Lost in Translation. That's the name of the paper. So if you have any question that you have time, I'm open now to questions. Otherwise, you can reach me out over Twitter. Mbite is my handle for questions. And thanks for attending.